This problem says to calculate the osmotic pressure of a 0.012 molar solution of sodium chloride in water at 0 degrees. Assume the Van Hoff factor is 1.94 for this solution. Okay, so the Van Hoff factor, of course, is just based on the separation of those ions, so that because this is a colligative property, it's only dependent on the number of solute particles, and when sodium chloride dissolves you get 2 particles. Okay, it's actually in reality slightly less than 2 because some of those charged particles may still cling together. So this is the number that we will be using, slightly less than the 2, but just based on the number of ions that are actually in the solution, or rather the number of solute particles, independent particles. All right, so we're talking about osmotic pressure. So the equation we're going to use there is pi equals CRT, where capital Pi is the osmotic pressure, and then here is the concentration in molarity. Okay, so and that is the solute concentration, the concentration of solute particles. And then we have the gas constant and the temperature. All right, so here is the information that they gave us. The gas constant R 0.0821 liter atmospheres per mole Kelvin. All right, so this kind of defines our units for us. The molarity, of course, cancels out with the moles and the liters. We need Kelvin here, so we're going to add 273, and that, of course, is 273 Kelvin. Okay, and then we'll find the pressure in atmospheres. But first, let's look at this concentration, right? Because that's the concentration of NaCl, but my real concentration, my concentration of solute particles, is going to be 1.94 times that amount. Okay, because on average 1.94 particles are generated for every NaCl unit. All right, so we're just going to multiply this by 1.94 to get the concentration there, and then we'll multiply by 0.0821 liter atmospheres per mole Kelvin, and we'll multiply by the temperature. Okay, 273 Kelvin. All right, so just plug it all on in the calculator, and what we end up with is 0.012 times 1.94 times 0.0821 times 273. Okay, and what we have is 0.52, I believe we had 3 significant figures there, so 0.522 atmospheres, right? And if you wanted to convert that to millimeters mercury, or torr, it would be 396.6. Okay, but that is the osmotic pressure for this solution.